Here we are, Friday. We have two topics today. These are two kind of interesting forces that we're going to explore. Again, don't forget we're in the business of model building. So these two forces provide something different in each case, and they do different things for our modeling, trying to understand the motion. So when you're thinking about friction, you're reading about friction, really three kinds that you want to distinguish. There's static friction, kinetic friction, and this rolling friction. So when you think about friction, one of the things that you're going to want to think about is that the amount of friction really depends on how much pushing or pulling is going on. Okay? So as an example, if I put my hand on the board, okay, well, if I don't push too hard, my hand kind of slides down. So what I do is I set my feet and I push on the board, and now I feel that static friction. Okay? But still, if I try to push up hard enough, at some point my hand's going to slip, and kinetic friction, that is friction of motion, wins the day. So pay close attention to this. As you read, as you look at the examples, try to quantify what you're seeing. So static friction, for instance, is really interesting. Okay? Slide 36 and 37 have some interesting qualitative character for static friction, but try to quantify it. Try to plot in some reasonable fashion for you what those qualitative characters mean. Now, we'll work some examples in class and talk more about this, but you should give it a shot. It'll make our class discussion more meaningful for you. Drag is our second topic. Okay, so drag is, I think, one of the most interesting and fun forces to work with. Okay, it's kind of an advanced topic, but one that kind of lends itself nicely to modeling in certain cases. So I want to take a few minutes and just maybe guide your thinking on drag. So first of all, let's draw a picture. Let's pretend like I have a ball traveling through the air, and maybe I've thrown it at some earlier date, and maybe my velocity at that time looks like this, okay, kind of up and to the right. Well, at that time, I know that gravity acts downward, but I also have this drag force. So this drag force acts in the opposite direction as my velocity. And this will always be the case. So this force is going to depend on time, where I am in the motion, and what my velocity, what my speed are. Right? So if you want to quantify this, I encourage you to think about it two ways. The drag force, well, the constants are defined in the book, depending on the density of the air and the surface area. But I like to just put all that stuff into a constant. Okay, so again, the area, the cross-sectional area is in there, the density of the fluid or the air is in there, etc. So there's a bunch of stuff in there. And then the way I'm going to write this is it has magnitude v squared, so the speed squared, and it points in the minus v hat direction, that is in the opposite direction as the velocity. And if you don't like that, write it like this. I like to write it actually this way. It's that constant, c there, the speed, and then it's in the opposite direction as the velocity, opposite direction as the velocity. So you can write it in a couple different ways. It's proportional to v squared, the speed squared, and points in the opposite direction as the motion at any one time. So if we look at these forces, let's just again do the simple example of a ball, say traveling through space. If I want to write down Newton's second law, F net is equal to ma. Well, if I enumerate the forces without breaking them down into x and y, okay, well, what I get here is I get my drag force plus mg equals ma. Now that's going to be the general case. But let's be more specific here. Let's say that we have a ball dropped in the minus y hat direction. That is, let me call y hat up, okay? To use spelling, got that, okay? What this means is that I take the ball and it's going to travel downward. So my velocity at any given time is going to point downward. But looking at it like this, well, my velocity is downward, then at any given time, my drag points up and mg points downward. So if I were to write down Newton's second law, F net in the y direction is equal to ma. This is in the y direction now. Right? Well, I have two forces. I have a positive drag force, right, which is going to be cv squared. Okay, notice the minus sign goes away now because I've explicitly determined the direction here. And gravity, mg, points downward. So it's in the negative direction. It's equal to ma. So here's our Newton's second law. The solution to this equation would govern the motion. Now, we're not going to solve it right now, but I just want to point to a couple things here, right? So first of all, this term starts at 0, because initially the speed is 0, but it grows. And it's always going to be positive. This term is constant. Okay? Gravity is constant. So what I end up with is I end up with two forces. One of them is constant and negative, the other one that's positive and growing. And what's going to happen is that term over here is going to grow and grow and grow until it matches gravity. At that point, the acceleration becomes 0. If I were to plot this out, okay, if I were to plot the acceleration as a function of time, well, what would it look like? Well, initially, when my speed is 0, my acceleration is going to be minus g. But over time, what's going to happen is this thing is going to kind of grow and approach 0. It's never going to quite reach 0. It's going to be smoother than I drew, of course. But as this term gets larger and larger and more positive, we reach 0 acceleration. And so at the acceleration equal to 0, that's when I reach the so-called terminal velocity. Now I can actually find what it is, because when the acceleration is 0, cv squared minus mg is equal to 0. Or, if I rearrange a little bit, the terminal velocity is going to be the square root of mg over c. I'm going to box this up for you. Stare at this. Okay, it's in your text. Now I simplified it a bit. Okay, but you could plug in what this constant is based off of the reading. Think about what this means. Okay? Try to make a sort of a proportionality argument. As I increase the surface area, what happens? As I decrease the density, what happens to the terminal velocity? Okay? Try to make some quantitative predictions about what you expect. And again, as always, take your time, be patient. Some of these things may be new and challenging, but don't hesitate to come and ask a question. I'm excited about this topic. It's fun for me, and I hope that it's fun for you.